Welcome to Mathematical Physics. Today, we are going to explore a foundational concept known as initial value problems. If you have ever wondered how physicists can predict the exact trajectory of a rocket or the precise motion of a pendulum, the secret lies right here. We are going to learn how combining the general rules of nature with specific starting conditions allows us to pinpoint the exact future of any physical system. Let us dive in. To understand why this concept matters, imagine you are trying to predict the future path of a thrown baseball. If you only know the general rules of gravity and air resistance, you can determine the overall shape of the path, which is a parabola. But that is not enough. To know exactly where this specific baseball will land, you absolutely must know exactly where it was thrown from and how fast it was moving at the very beginning. Without these starting facts, you only have a vague idea of what might happen. Now that we have a physical picture, let us look at the mathematics. In mathematical physics, the rules of nature are written as differential equations. When we solve these equations, they give us a general family of possible solutions, which contain unknown constants. An initial value problem, or IVP, is simply a differential equation paired with a specific set of starting conditions. These starting conditions allow us to pin down the exact physical reality of our system by finding the specific values for those unknown constants. With them, we get a precise, unique prediction. Building on that definition, let us see how this works for a first-order system. When you solve a standard first-order differential equation, the integration process naturally introduces an arbitrary constant, often denoted as c. Because c can be any number, the solution is not just one curve, but an infinite family of parallel curves. To select the single correct curve that represents our specific physical situation, we are given an initial condition. This condition specifies the value of the unknown function at a particular starting point, usually at time 0. This brings us to the formal mathematical expression of a first-order initial value problem. Conceptually, this formula combines the general rule of change with a specific starting snapshot. The first part is the differential equation itself, telling us how the system changes over time. The function f dictates the rate of change of our variable y with respect to time t. If the rate of change increases, the curve gets steeper. The second part, separated by a comma, is the crucial initial condition. It explicitly states that at the specific starting time, t0, the value of our function y is exactly y0. If we change y0, we shift the entire physical trajectory to a new starting point. Before we move on, let us see how we actually use this formula in practice. We are given the differential equation and the starting values. First, we solve the differential equation to find the general solution, which will include our unknown constant c. Next, we plug in t0 for time and y0 for our function. Why do we do this? Because it creates a simple algebraic equation where the only unknown left is that constant c. We then solve for c. Finally, we plug that specific value back into our general solution. This final answer represents the unique, concrete physical trajectory of our system, completely free of any unknown variables. Now that we have solved the equation algebraically, let us visualize what we just did. Look at the graph on your screen. The horizontal axis represents time t, and the vertical axis represents our variable y. Notice all those faded, light gray, wavy lines? Those represent the infinite family of parallel curves generated by the differential equation alone, each with a different constant c. Now look at the bold blue line. The black dot labeled initial condition at t0, y0 is the exact starting point we were given. By forcing our solution to pass through that specific dot, we anchor the system, selecting the single dark blue curve as our true physical reality. Having mastered first-order systems, we must now step up to something even more common in physics. We very frequently deal with second-order differential equations. Why? Because of Newton's second law of motion. This fundamental law involves acceleration, and acceleration is the second derivative of position with respect to time. Because it is a second-order equation, finding the solution requires us to integrate not once, but twice. This mathematical reality fundamentally changes how we must approach the initial conditions of our physical system. This requirement to integrate twice leads us to an important realization. When we integrate twice, our general solution will naturally contain two arbitrary constants, which we can call C1 and C2. Therefore, a single initial condition is no longer enough to determine the exact physical state of the system. To solve a second-order initial value problem, we must be provided with two distinct initial conditions at the exact same starting time. In a mechanical system, these two conditions correspond to knowing both where the object starts, its initial position, and how fast it is moving initially, its initial velocity. Let us look at the mathematical formula for this situation. This equation represents a standard second-order linear initial value problem, incredibly common in studying harmonic oscillators or electrical circuits. Conceptually, it balances the internal forces of the system against an external driving force. The term with the second derivative represents acceleration. The function g of t is the external driving force. If the driving force increases, the system's response will amplify. Notice we now have two conditions at time t0. The first condition, y of t0, is the starting position. The second condition, y prime of t0, is the starting velocity. Both are required to lock down the two integration constants. Now that we have our second-order formula, let us walk through how to solve it. We are given the differential equation, the initial position, and the initial velocity. First, we find the general solution, which contains our two unknown constants. Next, we substitute the initial position into this general solution to get our first algebraic equation. Then, we take the first derivative of our general solution and substitute the initial velocity into it, giving us our second algebraic equation. Why do we do this? Because we now have a system of two equations with two unknowns. We solve this system to find the exact values of both constants. The final answer is the unique physical trajectory of the object. We have covered a lot of ground today, so let us review the key takeaways. First, remember that differential equations alone only provide a general family of possible solutions. It is the initial conditions that pin down the exact physical reality of a system, allowing us to make precise predictions. Second, a first-order problem requires just one initial condition to find its single integration constant. Finally, because physics relies heavily on second-order equations, like Newton's laws, we often need two conditions, typically initial position and initial velocity, to fully determine the system's future. You now have the foundational tools to predict physical motion.